Hey, what's up everybody? My name is Hassan and welcome to this 10-minute introduction to hypothesis testing, which is one of the most valuable tools for research in any discipline, whether it's engineering, biology, medicine, or computer science. It's an essential tool that you must know. So without further ado, let's get to it and I'll see you in there. Hypothesis testing allows you to examine whether the change that you observe in your data is caused by some real underlying change, or is it the consequence of some random variation. Now, let's suppose you have a group of students whose average score on a certain test is equal to 60. Now the school decides to offer some extra coaching classes, at the end of which the students retake the exam, and we discover that the average score increases from 60 to 65. Now it is possible that this increase in the average test score is caused by a genuine increase in the scores of all students. But there's also another possibility. It is possible that two of the students do exceptionally well on the new test, but all the other students are pretty much at the same level. Now in this case, would it be fair to claim that the extra coaching classes were responsible for the increase in the test scores? These are the sort of questions that hypothesis testing allows you to answer. Decisions in hypothesis testing are typically based on the test statistic, which is given by the formula highlighted in yellow. It enables us to quantify how much our observed data deviates from the value expected from a null hypothesis. Hypothesis testing starts by identifying what are called critical points. Critical points enable us to divide the distribution into an acceptance region where we accept the null hypothesis and a critical region where we reject the null hypothesis. A test in which critical regions lie on both sides of the acceptance region is referred to as the two-tailed hypothesis test. We also have the one-tailed hypothesis test, which is further subdivided into the left-tailed test, in which the critical region is below the distribution mean, and the right-tailed test, in which the critical region is above the distribution mean. Now let's go through an example. An engineer in your company claims to have improved the heat tolerance of an existing alloy. The heat tolerance of the existing design is Gaussian distributed with a mean value of 1500 Celsius and a standard deviation of 45 Celsius. The engineer has produced 9 samples using the new design whose heat tolerance was measured to have a sample mean of 1550 Celsius. Assuming the standard deviation remains unchanged, can we accept the engineer's claim that heat tolerance has improved? As a first, we're going to highlight the relevant information in this example. So we have a Gaussian distribution with a mean value of 1500 Celsius and a standard deviation of 45. So let's plot the data distribution. So our mean value is 1500. One thing that you should note is that the standard deviation that you will use in this case will be equal to the given standard deviation divided by square root of the number of samples. So you will use 15 instead of 45. We want to examine whether the heat tolerance has improved. So let's set up the null hypothesis. You should note that the null hypothesis is typically the status quo, or the hypothesis that you are trying to disprove, which in this example is that heat tolerance does not improve in the new design. So now that the null hypothesis is set, we can go ahead and find our critical value. The critical value is typically based on a significance threshold alpha. The significance threshold represents the amount of probability mass in the critical region. And typical values of alpha, or the significance threshold, are 1% or 5%. We can find the critical value either from probability tables or using the Python command below. Now note that the norm.ppf method gives us the CDF of the distribution. Therefore, we set its argument to be 1 minus of the alpha value instead of directly giving the alpha value, which is 0.01. We now have the critical value and it's approximately 2.33. In fact, this is what I would call the normalized critical value, and it tells us that the actual critical value is 2.33 standard deviations above the mean value. We can convert this into the critical value corresponding to the actual units of the data, and that turns out to be around 1535, as you will see on the next slide. And yes, you can see that it is in fact actually equal to 1534.89, which is around 1535. Now, since the observed sample mean of 1550 is greater than the critical value, it lies in the critical region. Therefore, we can go ahead and reject the null hypothesis, which was that there is no improvement in heat tolerance. An alternate method to solve this example is to find the t-statistic and compare its value with the normalized critical value. The test statistic also indicates that the null hypothesis can be rejected because its value exceeds the normal critical value. Let's now take a look at another similar but slightly different example, which states that you are experiencing hair loss and skin discoloration and think that it might be because of selenium toxicity. You decided to measure the selenium levels in your tap water once a day for 1 week. Your results are given in the table below. The EPA maximum contaminant level for safe drinking water is about 0.05 mg per liter. Does the selenium level in your tap water exceed the legal limit? Assume an alpha value of 0.05. The null hypothesis in this case would be the status quo, which is that the levels do not exceed the limit. The alternative hypothesis, therefore, would be that the levels do exceed the limit, and then we can use the data given in the table and the statements to find the sample mean and the sample variance, and then from these we can determine the t-statistic, which comes out to be 2.17. Now I want to pause here for a second and point out one subtlety. You should note that here we're using the t-statistic and the t-distribution in this example. Now this is different from example 1, where we used the z-statistic and the z-distribution, and there's a very good reason for that. In the previous example, if you go ahead and see, you actually knew the standard deviation of the data, but we do not know it here. In fact, we have to determine it from the data, which we did on the previous slide. So a general rule of thumb that you should be using is you should use the z-statistic when the population standard deviation is known to you, but if you don't know it, then you should opt for the t-statistic, which is determined from the data samples. We can now find the critical value of the t-distribution with the alpha value equal to 0.05 and a degree of freedom equal to n-1, which is 6. Again, you can use probability tables or Python. If you use Python, you can use this command. You need to supply the degree of freedom as an additional argument. You can see that the critical value is 1.94. If you compare that with your t-statistic, it's smaller. Therefore, you can go ahead and reject the null hypothesis. Two-sample hypothesis testing. The cases that we've seen so far are examples of the one-sample hypothesis testing. But there's another important category which is called the two-sample hypothesis testing, and it examines whether there's a difference or there's a significant difference between the means of two populations. And this is something which can be very important when, let's say, you're doing some sort of a control study, you're examining a new drug and you're trying to test its efficacy. So you would have maybe a control group that gets a placebo, and then another group which gets your trial drug, and then you try to see if there's a significant difference in the health outcomes of the control group and the treatment group. And I'll talk about that in more detail on the next slide. It has two subcategories. The first one is the paired two-sample test. The second one is the unpaired two-sample test. So let's quickly take a look at some of the key differences between the paired and unpaired two-sample tests. With the paired test, each value in one population corresponds directly to a value in the other population. Whereas in case of the unpaired test, both populations are assumed to be independent. Now, with the paired test, One example can be the before and after values of test subjects undergoing a certain drug treatment. So you could monitor some health factors such as maybe sugar levels before you give your subjects a certain drug, and then you can monitor these same levels on the same subjects after you give them your trial drug to see if there was a significant difference between the before case and the after case. Another example could be computer vision, where you're trying to compare the baseline performance or the performance of a baseline semantic segmentation algorithm with some new novel semantic segmentation algorithm that you developed. Now, it's not just enough or rigorous enough to say that, you know, the average value of your novel scheme is better than the average value of the baseline. It would be far more better or statistically more rigorous if you demonstrated that there was a statistically significant difference between the two on, let's suppose, a fixed set of test images. Unpaired test, very important example could be examining the impact of a candidate vaccine on a control group and a treatment group. Now, as far as the procedure is concerned, I've put that here, but I'm not going to go into the details of this. You can read up the procedure for the paired test and for the unpaired test later on if you're interested. Now, there's a quick word that I want to say about the assumptions that are made for hypothesis testing. Application of hypothesis testing described in these slides assumes that your dependent variable is approximately normally distributed, and that generally works in a lot of cases, but it's always a good idea to actually apply a test of causality or normality before you start applying these hypothesis tests. Now, here are some tests that you could actually use to test if your data is normally distributed, and then if in case your data turns out not to be normally distributed, then what you could do is maybe go for a non-parametric hypothesis testing approach instead of the t-test, and some of those approaches that you could use in that case are also listed on these slides. So thank you very much for watching this lecture. Here are some of the references that I used. Thank you, and hope you liked the lecture.